Imagine two particles born together in the fiery heart of a star. As they journey across the cosmos, they remain mysteriously connected. This bond, known as quantum entanglement, is one of the most fascinating phenomena in the universe. In the strange world of quantum mechanics, particles behave in ways that defy common sense. They can influence each other instantly across vast distances. This spooky action at a distance, as Einstein called it, has baffled scientists for decades. So how does entanglement work? It all starts with the concept of superposition. In the quantum world, particles don't have definite properties until they are measured. Instead, they exist in a blurry cloud of possibilities, a superposition of states. Imagine a spinning coin, neither heads nor tails until it falls flat. That's superposition. Now imagine two spinning coins, linked so that when one falls on heads, the other instantly falls on tails, no matter how far apart they are. That's entanglement. This instant connection is the spooky part that bothered Einstein. He believed that nothing, not even information, could travel faster than light. Yet, entanglement seemed to violate this fundamental principle. The implications of entanglement are profound. It suggests that the universe is interconnected in ways we are only beginning to understand. It challenges our notions of locality, the idea that objects can only be influenced by their immediate surroundings. Entanglement opens up the possibility of instantaneous communication, teleportation, and even a deeper understanding of the very fabric of reality. It is a concept that stretches the mind and inspires wonder about the true nature of the cosmos. Einstein, despite his groundbreaking work in quantum mechanics, was deeply troubled by entanglement. He famously called it spooky action at a distance and believed that it pointed to a fundamental flaw in our understanding of the universe. He argued that the universe couldn't be so random, so unpredictable. There had to be some hidden variables, some underlying mechanism that explained this seemingly instantaneous connection. This debate between Einstein and Niels Bohr, another giant of quantum mechanics, raged for decades. Bohr argued that we had to accept the strangeness of the quantum world, that reality was inherently probabilistic. Einstein, ever the realist, refused to accept this interpretation. He spent years trying to find a way to explain entanglement without resorting to spooky action. This debate, though unresolved during their lifetimes, pushed the boundaries of our understanding and led to new experiments and insights. It highlighted the fundamental questions about the nature of reality that quantum mechanics raises. The debate over entanglement remained a philosophical one until the 1960s when physicist John Bell devised a way to test it experimentally. Bell's theorem, as it came to be known, provided a set of inequalities that could distinguish between the predictions of quantum mechanics and those of any theory based on local realism. In simpler terms, Bell's theorem gave us a way to see if the spookiness of entanglement was real or just an illusion caused by our limited understanding. Experiments based on Bell's theorem were conducted in the 1970s and 1980s, and the results were clear. Quantum mechanics was right. Entanglement was real, and the universe was indeed stranger than we could have imagined. These experiments were a turning point in our understanding of quantum mechanics. They showed that the universe was not bound by our everyday intuitions. The spooky action at a distance that Einstein found so unsettling was a fundamental aspect of reality. The implications of these findings are still being explored, but they have opened up new avenues of research in fields like quantum computing, quantum cryptography, and our understanding of the nature of space and time. Section 5. Beyond the lab quantum entanglement in action. For decades, entanglement remained confined to the realm of theoretical physics, a bizarre curiosity with no practical applications. However, in recent years, scientists have begun to harness the power of entanglement for technological advancements. One of the most promising applications is in the field of quantum computing. Traditional computers store information as bits, which can be either 0 or 1. Quantum computers, on the other hand, use qubits, which can be in a superposition of states both 0 and 1 simultaneously. Entanglement is crucial to quantum computing because it allows qubits to be linked together, even when physically separated. This allows for a massive increase in processing power, with the potential to revolutionize fields like drug discovery, material science, and artificial intelligence. Imagine a computer that could solve problems in seconds that would take classical computers years, even centuries, to crack. That's the promise of quantum computing. And it's not just computing power that entanglement offers. This spooky phenomenon also holds the key to unbreakable encryption, instantaneous communication across vast distances, and even teleportation. Section 6: Quantum Computers, a revolution in computing power. Let's dive deeper into the world of quantum computers. Imagine a computer so powerful it could simulate complex molecules leading to life-saving drugs, or crack encryption codes protecting our sensitive data. These are just a few potential applications. Unlike classical computers, quantum computers use qubits. Qubits can exist in a superposition of states. This allows for exponentially faster calculations. Tasks taking classical computers billions of years could be done in minutes. Quantum computers hold immense promise for medicine, AI, and cryptography. They could revolutionize our world in unimaginable ways. Imagine eradicating diseases and creating new materials. This is the future quantum computers could unlock. Section 7: Unbreakable Codes, Quantum Cryptography for a Secure Future. In an increasingly interconnected world, the security of our data is paramount. From online banking to sensitive government communications, we rely on encryption to protect our information from prying eyes. However, traditional encryption methods are not foolproof. As computers become more powerful, the codes we use today may become vulnerable to hacking in the future. This is where quantum cryptography comes in. By harnessing the power of entanglement, quantum cryptography offers a way to create unbreakable codes, ensuring the security of our data for generations to come. How does it work? Imagine two parties, Alice and Bob, who want to share a secret message. Using quantum entanglement, they can generate a shared key that is completely random and known only to them. Any attempt to intercept or eavesdrop on the key would instantly disturb the entangled particles, alerting Alice and Bob to the intrusion. This makes quantum cryptography incredibly secure. Unlike traditional encryption methods, which rely on mathematical algorithms that could be broken by a powerful enough computer, quantum cryptography relies on the laws of physics themselves. With quantum cryptography, we can create a future where our data is truly secure, protected by the unbreakable laws of the quantum world. Section 8: Redefining Reality. Entanglement's implications for our understanding of the universe. Quantum entanglement is not just a technological curiosity, it's a profound mystery that forces us to confront the very nature of reality. It challenges our everyday intuitions about space, time, and the nature of information. The idea that two particles can be instantaneously connected regardless of distance suggests a universe that is far more interconnected than we ever imagined. It hints at a deeper level of reality, where the boundaries between separate objects become blurred. Some physicists believe that entanglement could be the key to unifying quantum mechanics with general relativity, Einstein's theory of gravity. These two pillars of modern physics have been notoriously difficult to reconcile, but entanglement could provide the missing link. Others speculate that entanglement could play a role in explaining some of the most puzzling phenomena in the universe, such as the behavior of black holes, the origin of the universe, and even the nature of consciousness. While these ideas remain highly speculative, they highlight the profound implications that entanglement has for our understanding of the universe. It is a concept that continues to push the boundaries of our knowledge, forcing us to rethink our place in the cosmos. Section 9: The Entangled Future, Unraveling the Mysteries of a Connected Cosmos. As we delve deeper into the quantum world, we are only beginning to scratch the surface of what entanglement can teach us. This spooky action at a distance holds the key to unlocking some of the greatest mysteries of the universe, from the nature of space and time to the origin of the cosmos itself. The future of entanglement research is bright, with new discoveries and applications emerging all the time. Quantum computers are poised to revolutionize fields like medicine, materials science, and artificial intelligence. Quantum cryptography promises unbreakable codes, ensuring the security of our data in an increasingly interconnected world. But perhaps the most exciting aspect of entanglement is its potential to fundamentally change our understanding of reality. It challenges our everyday intuitions, forcing us to confront the strange and wonderful world of quantum mechanics. As we continue to explore the implications of entanglement, we can expect to uncover even more surprises, pushing the boundaries of our knowledge and revealing the true nature of our interconnected cosmos. The universe is full of wonders, and entanglement is a shining example of the mysteries that await us as we continue to explore the vast unknown.